Hey, good to have you here for this episode. Today we're diving into something pretty fascinating, levitating tiny objects without any physical contact. Ever heard of a micro-machined hybrid contactless suspension?
That sounds intriguing. So like a tiny object just floating in midair? How does that even work?
Exactly. Imagine a tiny metal disc just hovering, held up by invisible forces. This device, called a micro-HCS for short, uses a mix of magnetic and electrostatic forces to levitate a small conductive disc, what they call a proof mass.
Oh, I see. So it's not just magnets but also electric fields working together. Why combine both? Wouldn't magnets alone be enough?
Good question. The hybrid approach actually gives more control. Magnetic levitation alone can keep the disc floating, but adding electrostatic forces lets you adjust how stiff or springy the levitation feels, especially vertically. It's like having a fine-tuned balance between push and pull.
That makes sense. And I guess at such tiny scales, friction is a big problem, right? So levitating parts without touching anything would help avoid wear and tear.
Exactly. In micro machines, think sensors, tiny motors, and actuators, friction dominates over inertia, which messes with performance and longevity. So contactless suspensions like this solve a fundamental issue.
So how is this device actually built? I mean, what does it look like?
The prototype they made is about 9 millimeters square and less than 2 millimeters thick. It's like a tiny sandwich made of 3 main parts: a coil structure with 2 micro-coils, one for levitation and one for stabilization, a bottom electrode structure, and a top electrode structure.
And the disc, the proof mass, is where in this sandwich?
It's levitated right between the top and bottom electrodes, about 150 micrometers above the coil structure. The disc itself is aluminum, about 3 millimeters across and just 30 micrometers thick.
Wow, that's really small. So the coils create a magnetic field to levitate the disc, and the electrodes create an electric field to adjust its position and stiffness?
Exactly. The electrodes on top and bottom apply a voltage, generating an electrostatic field that can push or pull on the disc, adjusting its vertical stiffness. Plus, there are additional electrodes that sense the disc's vertical displacement by measuring changes in capacitance.
So it's like the device can feel where the disc is and apply forces to keep it stable?
Yes, it operates in a force rebalance mode, similar to how some accelerometers work. They even use a laser sensor during experiments to measure the disc's position precisely.
That's pretty clever. But I remember you mentioned something called pull-in instability. What's that about?
Pull-in instability is a key limitation in electrostatic systems. Basically, as you increase the voltage on the electrodes, the electrostatic force pulling the disc grows stronger. At some critical point, this force suddenly overcomes the restoring forces, like the magnetic levitation and mechanical stiffness, and the disc snaps down onto one of the electrodes.
So it's like pushing a hoverboard closer to a charged plate, and at some point, it just sticks to it?
Exactly. That sudden snap is the pull-in. It limits how much you can reduce stiffness or adjust the position, because pushing too far causes collapse.
And I guess in this hybrid system, with both magnetic and electrostatic forces, the pull-in behavior is more complicated?
Right. The magnetic forces add nonlinearities, so the classic pull-in models don't fully apply. The researchers developed an analytical model to capture this complexity.
Speaking of the model, how do they actually describe the forces and stability mathematically?
Well, they treat the levitated disc as influenced by magnetic energy from the coils and electric energy from the electrodes. The induced currents in the disc, called eddy currents, are complex, so they approximate them as 2 main current loops to simplify the math.
That sounds like a smart way to handle complexity.
It is. They use generalized coordinates to describe vertical, lateral, and angular displacements, but focus mainly on vertical motion, since that's most relevant for the accelerometer application.
And the model balances gravity pulling down, magnetic levitation pushing up, and electrostatic forces adjusting stiffness?
Exactly. The model includes nonlinear terms and uses special mathematical functions, elliptic integrals, to describe mutual inductance between coils and eddy currents. To make it more manageable, they propose a reduced model approximating the mutual inductance with a logarithmic function, which is accurate within a small error margin.
So this reduced model lets them analyze when the system becomes unstable, like predicting the pull-in points?
Yes. They identify 2 pull-in points, one where the disc snaps toward the top electrode and one toward the bottom electrode.
Interesting. Did they test this prototype experimentally?
They did. Using the coils, they levitated the aluminum disc at about 150 micrometers height. By applying voltage to the electrodes, they successfully decreased the vertical stiffness by about 25%.
That's a significant change. How did they measure that?
They used capacitive sensing with electrode pairs to detect displacement and a laser distance sensor for precise position measurement. They plotted force against displacement and confirmed the stiffness reduction matched theoretical predictions.
So the electrostatic field actually generated a negative stiffness component?
Exactly. The electrostatic forces reduced the overall stiffness, making the levitation softer. The model predicted this negative stiffness, and the experiments confirmed it.
And the model suggests they could reduce stiffness by up to 2 orders of magnitude before hitting pull-in?
Yes, theoretically. That means the levitation can be made very soft, which is great for improving sensitivity in sensors like accelerometers.
That's impressive. So why does all this matter for the future of micro devices?
Well, micro-machine contactless suspensions are key to next-generation sensors and actuators. Reducing friction and precisely controlling stiffness improves accuracy and device longevity.
And the hybrid approach combines the best of magnetic and electrostatic suspensions, offering adjustable stiffness and stable levitation.
Exactly. Plus, understanding pull-in instability helps engineers design devices that operate safely near their performance limits without sudden failure.
I like the analogy you mentioned earlier, the levitated disc as a tiny hoverboard floating between magnets below and charged plates above.
Yeah, the magnetic field keeps it floating, and the electric field gently pushes or pulls, adjusting how springy it feels. But if you push too hard with the electric field, the hoverboard snaps down onto a plate that's pull-in instability.
And these researchers built that tiny hoverboard, measured how it moves, and mapped out when it might snap down.
Exactly. That knowledge lets them design better, more sensitive devices that float safely and respond precisely to tiny forces.
It's amazing how controlling such tiny forces can have big impacts on sensor technology.
Absolutely. So, to sum up, this work shows a practical prototype and a solid theoretical framework for micro-machined hybrid suspensions, demonstrating controllable stiffness and identifying pull-in limits.
And that opens doors for more reliable, sensitive microsensors and actuators in the future.
Well said. Thanks for exploring this with me today.
Thanks, it was great diving into this. Looking forward to the next one.